So our first attempt to get some information, some calculations on the physical properties of the spring in the car, which one we want to use to store energy in, wasn't very useful using the spring characteristic. But if we would use the tensile curve of a material, maybe we could go a little further. Let's take a look at the tensile curve of steel. The tensile curve of steel is this diagram, where vertically at the axis is the strain of the stress, and horizontally the strain, which are defined by the applied force divided by cross-section area, and the strain is the elongation divided by original length of a test bar. Well, let's first take a look at the test bar. That's usually something like this. If you have a test bar from steel, to make this diagram, you put this into a testing machine, and the machine will start to pull this piece apart. At first it will just elastically deform until this point where it will start to plastically deform until it snaps, it breaks. And then if you have this, then you will know a lot about this material, because this slope of this first part tells you something about the spring characteristics of this material. We wouldn't want to go beyond this point, because if a material plastically deforms, then there's no way you get the energy back that you put into it. So there's only one way to get your energy back, and that is stay in the elastic part of the curve. Okay, well, and if we stay in this part of the curve, it looks a little bit like the spring characteristic that we draw earlier. First, let me explain something about what's on the axis. This quantity stress is defined as force divided by cross-section area. This is the cross-section area, and the strain is defined by the delta L, the elongation divided by the original length, and this is the original length of the piece that is stretching. So this part is clamped into the machine, so the original length is L0. And why do we do this? Because if we would have a larger cross-section area, it would take a lot more force to tear this piece apart. So if we don't want this to influence the looks of our plot, of our graph, then we would need to normalize the vertical axis by dividing by the cross-section area. The same is done for the horizontal axis. If we would take a longer test bar, then it would stretch easier with lower force, and then it would be stretched in horizontal direction, and to compensate for this you divide by the original length of the test bar, so you get whatever test piece you put into the machine, if it's thick or if it's thin, if it's long or if it's short, you would get the same plot over and over again for the same material. That's, well, easier. That's better. In this plot, in this tensile curve for steel, you would see that this first part is a straight line, and it has a slope, and this slope is somewhat like the slope in the spring characteristic is an important part. It's actually a law. It's the Hooke's law, and it says that this E, this slope of this curve, is defined by stress divided by strain, or represented otherwise it's like a first order equation. Sigma, the vertical one, is the slope times the horizontal, and the way I want to use it is later on that I want to say that the slope of the strain is stress divided by the slope of this of this line. Well, the slope has a name. This E is the modulus of Young's modulus. Young's modulus. And for all materials, well, you can look them up in a database or find them on the internet. Mostly they're known values, and they just did this test to get these values. Well, let me now take a look at this graph here. If I take this area underneath this curve, is this now the same as in the other spring characteristic? Does this mean this is the energy that is put into the material by stretching it? Well, it's not exactly the energy. It's not the unit is not joule, because we divide here by cross-section area, and we divide by the original length. So in fact we divide by the total volume of the test bar, the total stretched volume, the total volume of the original test bar that is subject to stretching. And what would we get if we would calculate this area underneath the graph? Well, it's of course the energy divided by the volume. So it's like a specific energy. It's the energy you could store in 1 cubic meter of material. So that's specific energy. That's a very interesting one. We can even extend this one to specific energy with regards to mass, but we will do that later on. So let's say this is the energy per unit of volume. So that's what we get if we calculate this. And how much is this area? Well, it's of course a triangle because it's a straight line. So it's half times base, half times the strain times the stress. And the strain, I already said we are going to rewrite it a little bit into this one. So I will put this on the place of this strain, this epsilon, and we get the specific energy into the following formula. It's like sigma, the stress squared, divided by 2 times E. And this is in the unit joule per cubic meter. So this is a very important part. We can express for every material, if we know to what stress, to what yield stress, that's the yield strength. Let's call it sigma yield. If we stretch it to the yield strength, what energy is stored into the material is now, we can now calculate it. So to make it more useful even, we can make a specific energy with regards to mass, and we only have to add the density. So if we leave the formula in the same way, 2 times E, and we add the density, then we would have the unit joule per kilogram. So these are units and these are quantities. So now we have a very interesting formula, and in the next video I will fill in this formula for different materials, and we can maybe solve this problem that we said earlier. How much mass would I need to, spring mass would I need to store all the energy of a moving car at 72 kilometers an hour, 20 meters per second, to stop for a traffic light and then use this energy again to accelerate the car again. So this will be done in the next video with this formula. This is a very important formula for the specific energy of every material, and well, this will be done in the next video.